This video, we're going to be modeling with linear functions. More generally speaking, we're going to be solving application problems as they can be worked with linear functions. So there's three types of application problems we're going to work with. We're going to work with one type requiring a construction. We're going to work with another kind that requires intersections. And we're going to work with another variety that requires analysis of a particular equation. So first, we're going to work one with construction. We're going to find the area of the triangle bounded by the y-axis, the line f of x equals 4 minus 2/3 x, and the line perpendicular to f of x that passes through the origin. This problem is incredibly difficult without a drawing. So let's make a rough sketch. And it doesn't have to be a beautiful sketch, it just has to be a rough sketch. So we already know we're going to be finding the area of a triangle. Okay, as you recall, the area of a triangle is 1/2 base times height. And so we've got the line 4 minus 2/3 x. So the y-intercept is going to be 4, and it's going to be a negative slope. You'll see that that's actually not really important on the picture. So it's going to eventually end up hitting the x-axis. Now, we've got a line which is perpendicular to this equation, and it passes through the origin. So here's our origin, and we know that these are perpendicular, so they are in fact going to intersect. Now, what we want to do is find the area of the triangle bounded by the y-axis. Okay, we want to find the area of this triangle in particular. Okay, so first order of business. What's really nice about this is if I think about my triangle as, let me go ahead and just clear this out. If I think of my triangle as this being my height and this being my base, I'm already in pretty great shape because my height going from 0 to 4 is going to be 4. So right out of the gate, we're already halfway there. So now we've got to find the base. So for the base, what would be really nice to know would be this particular x value. Because if we know this x value, this distance is going to be our base. So what we want to do is find the point where they intersect. Now here's what's really tricky. How can I find the point of intersection of two lines when I don't even know the equation of the other line? I don't know the equation of this line, but I do kind of. It's passing through the point of origin, so I know the y-intercept is b. And I know that it's perpendicular to this equation, so the slope is going to be a negative reciprocal, so the slope is going to be 3/2 x. And I'm not going to say 3/2 x plus 0. I'm just going to get rid of the plus 0. So now what I want is the x-coordinate of their point of intersection. So what I'm going to do is set each of these equal to each other and solve for x. Now, from here, I could do a lot of fraction manipulation, but here's what I'm actually going to do instead. I'm going to get a little sneaky with it. So I see the denominators here. I'm going to write this as over 1. There's a 2 and a 1 and a 3. The least common denominator here is 6. So what I'm going to do is actually just multiply both sides of this equation by 6. And so when I do that, 6 cancels the 2 and changes this into a 3. 3 times 3 is 9x. And then I distribute the 6. 6 times 4 is 24. And then the 6 and the 3, again, that's going to cancel the 3, but it's going to change this to a 2. So 2 times 2 is 4x. And now I'm just going to go ahead and solve this equation. So I'm going to add 4x to both sides. And so I get 13x equals 24. Divide both sides by 13. And so now I get x is equal to 24/13. Great. So now I know that X value is 24 over 13. So that's going to be my base, which is what I was looking for in this triangle. Again, it is so egregiously clear that doing this without a picture would be really, really hard. So the 1/2 is going to cancel. It's going to change that 4 into a 2. And so now I have 2 times 24 over 13. 2 times 24 is 48 over 13. That's my area. This problem is tough. So take your time when you're working through this and build each part of this picture so that you have all of the information available to you to solve that particular problem. This is, obviously directly from your homework. Now, we're going to use intersections to solve a particular system. And this is going to mean that we are going to be building 2 separate equations given information. And from those 2 equations, we're going to discern their point of intersection, and that's going to be a thing that we're looking for. So we sell jewelry, and upon taking the job, we have 2 options of salary. We can either have a salary of $12,000 a year with a high commission rate, or a higher salary, just like a fixed rate, with a lower commission. So the question becomes, when is it more advantageous to take one over the other? So let's start with getting a model figured out for option A. So one thing you can always think about with your linear equations is, instead of thinking mx plus b as like slope and intercept, you could think of b as your starting point, and you could think of m as your rate, which is fine. So when I start to build this, I'm going to think of my rate. Well, my rate is 7% of my sales, and we'll say that X is just some dollar of sale. So the thing that helps us compute 7% is 0.07. And I'm starting with 12,000. Okay. I'm going to use the same sort of construction for B. I've got $21,000 a year, but a 3% commission. And now I want to know when option A is going to produce a larger income. So I need to know when they're going to produce the same income. And since A has a bigger rate, after that point is when you're going to see more return. Okay, so from the A option. So what we get to do is we're looking for where they intersect. So since we're looking for where they intersect, what we get creative license to do now is set each of these equal to each other. So what I'm going to do is move the x's over to the left-hand side. I don't know why. I just like that aesthetic better. I'm going to move my numbers over. So now I get 0.04x is equal to 9,000. All right, so now what I'm going to do is divide both sides by 0.04. And it's okay, brace for impact. This is going to be a big number. And one thing about real world problems is that we have a tendency to really want to dig into those, but we also want to dig into those in a way that we get nice answers. And that's not how it works. The real world is messy. Some of us know that too well. So 225,000 is the X value where they intersect. Now what's happening is, for every dollar beyond, well, every cent beyond $225,000, option A is yielding a better salary. So we need to sell at least $225,000. That's crazy to me. Worth of jewelry. for option A to be advantageous. Okay. Now for the last problem. This is what we're going to be doing here is constructing particular equations, and we're going to be analyzing those. So first piece of advice, think of the year 1950 as x equals 0, and think of each sort of x value as number of years after 1950. So it's going to make life easier for us to go ahead and just say x is 0 and x is 50 in this case, okay, just for our years. The first thing I'm going to ask you to do is figure out which one has a higher rate. So in order to do this, you're going to need to compute the slope. Go ahead and pause the video and compute the slopes for West Virginia and for Maryland. Okay, so let's do West Virginia first. So for West Virginia, what we really have are two coordinate pairs, 0, 3, 3, 200, and 50, 7, 2, 800. So we're going to use the slope formula to figure out our rate. So y2 minus y1 divided by x2 minus x1 All right, so let's go ahead and do these. I'm literally using the phone calculator right now. And we get 39,600 divided by 50. And we have a rate of 792. Okay, now what does that mean? That means each year beyond 1950, the median house home value in West Virginia is rising by $792. All right, now let's do Maryland. Again, we're going to set up our coordinate pairs. X is 0, 48,700. These numbers are so small for 1950. That is so crazy. And then 50, 146. Again, y2 minus y1. If you hear that in the background, that's my neighbor shouting to my dog, in case you were wondering. In recording videos, I've discovered that there's just nothing to be done about the sounds that exist in my home and in my orbit. So you may not necessarily know that I'm like a real person that exists, but you know that people talk to my dog. So there you go. Welcome to COVID land. So 146,000. Goodness gracious, I'm having a miserable time typing. Divided by 50, I get 1946. Okay. So here our slope is 1946, which means that every year beyond 1950 in Maryland, the median home rate is increasing by $1,946. So Maryland certainly has a higher rate. Okay. So let's just go ahead and document this, just so that we have it kind of at the ready here. You're going to see that I'm going to use a different notation tool here because I want to keep this on each slide. So for West Virginia, we had our rate was 792. And for Maryland, our rate was 1946. Okay. So we know which state has a higher rate now. And now we're assuming that the house values are changing linearly, which is a bit of a jump. But if these trends were to continue, what would the median home value in West Virginia be in 2010? So 2010, since we defined our years, our X values to be years beyond 1950, here we're saying X is equal to 60. So what would be really nice would be to have an equation for West Virginia in particular, so that we could just plug 60 into it and get what we need. Now, the problem we rub up against is, while we know the rate, we don't know what the y-intercept would be. Our rate is 792, but we don't know what the y-intercept is going to be. So let's start with the coordinate pair 0, 3, 3, 200 to find the b value, so that we could just plug 60 in for x. So x is 0. And I know my y value already is 33,200. And now this goes away, and what I'm left with is b is 33,200. Great. So if I made an equation for West Virginia, and let me use the annotation here, it would be y equals 792x plus 33,200. So this is going to be my equation for West Virginia. So now we're going to use that equation. We're going to plug x equals 60 into it. So having that equation is pretty handy. Since you already assumed that it was changing linearly, I don't see why it would be a bad exercise to just find the equations anyway, just right out of the gate. So let's assume that's the case. Again, be careful. We're not plugging 2010 in. If we plug 2010 in, we're saying that's 2010 years beyond 1950. That's certainly not the year 2010. All right, so now we're just going to go ahead and do the number crunching. I don't know if you can or not, but I'm hoping you can hear me like actually typing this into my phone in the background. And we get $80,720. That would be the median cost of a home in West Virginia in 2010. Okay. Now, we're going to assume that the trend existed before 1950 and continues after the year 2000. The state's two median house values will be or were equal in what year? The answer might be absurd. That just means that we may have to think about it for a second. So since they're going to be equal, what I want to do is set this equation equal to, I don't have this equation. So I'm going to have to make it. Fine. Not a big deal. I'm going to use the coordinate pair 0, 48,700. And I already know that the rate is 1946. So I'm going to say y equals 1946x plus b. Well, I already know that y is going to be 48,700. And I know x is equal to 0. That gets knocked out, so now I have that b is 48,700. So what I have now is the equation here. So now what I'm doing is I'm going to set this equation equal to this equation, and that's going to be how I will find out exactly when these things are equal. So let's do it. So we've got 792x plus 33,200. Now I understand that like I tend to like x's on the left just for aesthetic, and I'm left-handed, but I'm really not into negatives. So I'm going to go ahead and move this 792x over here. And then I'm going to move the numbers over to the left-hand side. I know, crazy. So now, what I have on my left-hand side is 33,200 minus 48,700. I get negative 15,500. All right. And then on my right-hand side, I've got 1946 minus 792. And I get 1154x. Now I'm going to divide both sides by 1154. And I get x is about equal to negative 13.43, bloody, 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 blah. So what this means is 13 years before 1950 is going to be where you've got the, is where you've got that equality. So you're actually going to need to kind of go backwards a little bit more. So think about like 0 on the number line. So 0's here, negative 13.43. We're only really looking for integer values because we want to know what year this was happening in. Okay, so we've got negative 14 and negative 13. So we would need to go with negative 14 because during this year is when it happens. So just based on how we define things, we define 1950 to be year 0. So to find out what year that is, we're going to do 1950 minus 14, and that's going to be 1936. Okay, I understand when it said the answer might be absurd, it feels absurd to have negative years, but since we defined our x to be 0, it's actually not an unreasonable thing at all. This is modeling with linear functions. Good luck on your homework assignment.